Hello there, and welcome to the Sleep with Science channel, where tonight we are going to do something a little different. Something that begins not with a question, but with a feeling. The feeling of standing completely still while the universe moves around you in slow, silent, impossible motion. The feeling of being so small that your entire life, every breath, every memory, every dream you have ever had, fits inside a single grain of sand on an endless, star-dusted shore. Settle in now. Let your body sink just a little deeper into whatever is holding you. Feel the weight leave your shoulders. Feel the quiet arrive. Because what we are about to explore tonight is one of the strangest, most beautiful, most mind-bending ideas that science has ever uncovered. An idea so vast and so quietly stunning that the moment you truly let it in, the world around you begins to feel a little different. A little softer, a little less urgent, and in the best possible way, a little less real. We are going to talk about time, but not time the way you usually think about it. Not clocks, not calendars, not the ordinary tick and talk of a Tuesday afternoon. We are going to drift into something far deeper than that. Something that physicists whisper about in equations and that poets have always felt in their bones without ever having the words for it. Something that has to do with speed and gravity and the astonishing possibility that time is not the same for everyone. That time can be stretched. That time can be slowed. That under the right conditions, in the right corner of the cosmos, a person could close their eyes, drift forward through space, and open them again to discover that hundreds of years have passed on the world they left behind. That entire generations were born and lived and loved and faded into memory while they simply floated, sleeping, breathing, dreaming, untouched by the centuries rushing past them like wind through open fields. This is not science fiction. This is science. And tonight, we are going to let it carry us. But first, we need to begin where all great journeys begin. Not at the destination. Not even at the door. We need to begin in the stillness before the first step. In the breath before the first word. We need to begin by understanding just how extraordinary the universe is that makes this strangeness possible. Right now, as you lie here, as the room holds you and the night wraps itself around everything like a dark velvet curtain, the earth beneath you is moving. You cannot feel it, but it is true. Our planet is spinning on its axis at roughly 1,000 miles per hour at the equator. And at the same time, it is orbiting the sun at approximately 67,000 miles per hour. And the sun itself, that ancient, burning, golden heart of our little solar system, is moving through the Milky Way galaxy at about 448,000 miles per hour. And the Milky Way is moving too, drifting through the larger fabric of the universe at speeds so enormous that numbers begin to lose their meaning. You are, in this moment, sitting perfectly still, and traveling faster than any human mind can genuinely comprehend. There is something deeply peaceful about that, if you let yourself feel it. You don't have to do anything. You don't have to go anywhere. The universe is already carrying you. It has been carrying you since the very first moment you arrived into this world, drawing your first breath of cool air, blinking up at a ceiling that was also, always, quietly hurtling through the dark. And in that darkness between the stars, that vast, ancient, breathtaking darkness, something incredible waits. Something that changes the rules of time itself. Something discovered not by a mystic or a dreamer, but by a theoretical physicist who worked in a patent office in Switzerland and spent his evenings thinking about what it would feel like to ride alongside a beam of light. Albert Einstein. A quiet man with extraordinary eyes and an even more extraordinary imagination. A man who looked at the universe and asked a question so simple and so devastating that it cracked the foundation of everything humanity thought it understood about reality. What if time is not fixed? What if the rate at which seconds pass, The speed at which your heartbeats count themselves out, the pace at which years accumulate into a life. What if all of that could change? What if time moved differently depending on how fast you were moving through space? What if it slowed, grew heavy and long and honeyed, the closer you came to something with enormous gravitational pull? He called it relativity, and the implications of that single, elegant, quietly revolutionary idea ripple outward in ways that scientists are still exploring more than 100 years later. One of those implications, one of the strangest flowers that bloomed from Einstein's garden of ideas, is something called time dilation. And time dilation is the doorway we are going to walk through tonight, slowly, softly, with no rush at all, into one of the most wonder-filled corners of the known universe. It begins with speed, with a particular, almost sacred speed of light. Light travels through the vacuum of space at approximately 186,000 miles per second. To put that in a way your resting mind can gently hold, if you could travel at the speed of light, you could circle the entire Earth 7.5 times. In a single second. One breath. One blink. 7.5 times around this whole spinning, breathing, living world before your eyes could even finish closing. And yet, as impossible as that sounds, as far beyond human experience as that number feels, it is the speed of light that becomes our compass tonight. Our guide through the deep and the dark and the strangely beautiful. Because here is where the story begins to bend. Here is where the universe reveals something about itself that feels almost like a secret. Something it has been holding quietly in the folds of space-time since long before there were any human minds around to wonder at it. When Einstein sat with his equations, when he turned the mathematics over and over in his hands like a smooth stone worn perfect by a river, he discovered something that stopped him. Something that must have felt, even to a mind as prepared as his, like standing at the edge of a very great height and looking down. He discovered that the speed of light is constant. Always. Everywhere. For everyone. No matter how fast you are moving, no matter what direction you are traveling, no matter whether you are standing still on a quiet hillside watching fireflies drift through summer air or hurtling through deep space at 90% of the speed of light, the speed of light remains exactly the same. 186,000 miles per second. Unchanging. Unwavering. Absolute in a universe where almost nothing else is absolute. And this one quiet stubborn fact, is what unravels everything. Because if the speed of light never changes, then something else must. If light always arrives at the same speed no matter how fast you chase it, no matter how fast you run toward it or away from it, then the universe has to balance its own equation somehow. And the way it balances that equation is by bending time itself. Let that land softly. Let it settle the way snow settles on still water, without splash, without disturbance, just a slow and gentle covering of something that was already there. Time bends. It stretches and compresses and flows at different rates in different places, under different conditions. The time you experience is not the same as the time someone else experiences. Not if one of you is moving faster. Not if one of you is closer to something with enormous mass. The universe does not run on a single clock. It runs on an infinite number of clocks, each ticking at its own quiet pace, some faster, some slower, some so different from the ones we carry in our pockets that they might as well belong to a different kind of reality altogether. This is not a poetic metaphor. This is not a beautiful way of saying something vague. This is a measurable, testable, demonstrated fact. Scientists have placed extraordinarily precise atomic clocks aboard airplanes and launched them around the world. Clocks that can measure time to billionths of a second. And when those clocks return to the ground and are compared to identical clocks that stayed perfectly still, they show different times. The ones that traveled, that moved through the air at hundreds of miles per hour above the gravitational pull of the Earth's surface, Those clocks are slightly, measurably, undeniably out of sync with the ones that never moved. Time passed differently for them. Even at the modest, gentle, human speed of a commercial airplane, time shifted. By a tiny amount, yes. By a whisper of a difference that you would never notice in a single lifetime. But the difference is real. The mathematics predicted it. The clocks confirmed it. And the implications, when you follow them outward into the deeper reaches of the universe, into the realm of stars and black holes and spacecraft moving at fractions of the speed of light, those implications grow from a whisper into something immense and breathtaking and almost too large to hold. Breathe with that for a moment. There is no need to rush. The night is long and deep and generously dark, and we are in no hurry at all. Let your breath slow down just a little more. Let the muscles behind your eyes relax. Let the thinking, planning, remembering part of your mind drift just slightly backward, like a boat leaving a dock, untethered now, moving gently on its own. Because what we are really talking about tonight, what lives at the heart of this strange and luminous idea, is the possibility of a journey unlike anything human beings have ever taken. A journey not just through space, but through time itself. Not by magic. Not by the turning of a fictional dial or the opening of a science fiction portal. But by the real, documented, mathematically precise warping of time that occurs when something moves fast enough, or falls deep enough into the well of a massive object's gravity. The universe, it turns out, is not a rigid thing. It is not a box with hard walls and a ceiling you can press your palms against. It is something far stranger and far more beautiful than that. It is a fabric. A living, responsive, almost tender fabric of space and time woven together into a single continuous surface that bends and curves and ripples whenever something with mass moves through it. Physicists call it space-time. And space-time, when you truly begin to feel it rather than simply think it, begins to feel less like a scientific concept and more like something you have always known. Something that lives not in the mind but somewhere older and quieter. In the body. In the breath. In that particular stillness that descends in the moments just before sleep, when the boundaries of yourself begin to soften and the world outside loses its hard edges and everything becomes a little more fluid, a little more possible, a little more vast than the daylight hours allow. Space-time is the stage on which everything happens. Every breath you have ever drawn. Every star that has ever burned. Every galaxy spinning slowly in the dark like a pinwheel left out in a cosmic wind. All of it happens inside space-time. All of it is shaped by space-time. And all of it, every last luminous thread of it, is affected by the two great forces that bend and warp and alter the fabric of that stage. Speed and gravity. We have touched speed already. We have let our minds drift gently toward the image of light crossing the void, constant and unwavering, while time itself rearranges itself around that constancy like water finding a new shape in a new vessel. But gravity is where the story deepens. Gravity is where the night gets darker and more beautiful. Gravity is where the universe begins to whisper things that feel almost too intimate, too close, too personal for something so inconceivably large. You know gravity already, of course. You have known it your entire life without ever being formally introduced. It is the thing that holds you to the earth. The thing that brings rain down through autumn air and settles fallen leaves along the edges of quiet roads. The thing that keeps the moon in its long, loyal orbit around this planet, and keeps this planet in its own faithful circle around the sun. Gravity is the most familiar force in all of human experience. And yet, Einstein looked at gravity and saw something that Newton, brilliant as he was, had not quite seen. Newton described gravity as a force, a pull between objects with mass, an invisible thread connecting things across distance. And that description works beautifully for most purposes. It gets satellites into orbit. It plots the paths of planets with extraordinary precision. It is one of the great achievements of the human intellect, and it will remain so forever. But Einstein went one step further. Einstein asked not just what gravity does, but what gravity is. And the answer he arrived at, the answer the mathematics led him to with a particular quiet insistence of deep truth, was this. Gravity is not a force pulling objects toward each other across empty space. Gravity is a curvature in the fabric of space-time itself, created by the presence of mass. When something with mass exists in space-time, it bends the fabric around it. It creates a curve, a depression, a gentle or not so gentle warping of the surface of reality. And other objects moving through that curved space-time follow the curves, not because they are being pulled, but because the path itself has been bent. A simple image might help. Imagine a stretched piece of silk, smooth and taut, shimmering faintly in dim light. Now imagine placing a heavy sphere at the center of that silk. The fabric dips. It curves downward and inward around the weight of that sphere, creating a depression that radiates outward in soft, concentric waves. Now roll a smaller sphere across the silk. It doesn't travel in a straight line anymore. It curves. It bends toward the depression. It follows the shape of the fabric rather than any invisible thread. That is gravity. That is what mass does to space-time. That is the architecture of the universe laid out in the simplest, most elemental terms that language can reach. And here is the part that carries us deeper into our journey tonight. Here is the part where gravity and time meet and something extraordinary happens in the space between them. The more massive an object is, the more deeply it curves space-time around it. And the more deeply space-time is curved in any given location, the more slowly time passes in that location. Time does not run at the same speed near a massive object as it does far away from one. Near something with enormous gravitational pull, time grows heavy. It thickens. It slows the way honey slows when the temperature drops, becoming dense and amber and reluctant to move. This is called gravitational time dilation. And it is not a small effect at the scale of truly massive objects. It is not a whisper or a fraction of a second. Near something like a neutron star or the edge of a black hole, the difference in the flow of time between that location and a distant, quieter region of space becomes staggering. Becomes almost beyond imagining. Becomes the kind of difference that could, under the right conditions, allow someone close to that massive object to experience only hours or days while years, decades, entire centuries unfolded for everyone and everything left behind. Let that image bloom slowly in your mind. Do not rush it. Do not try to grasp it all at once. Let it open the way a night flower opens, petal by petal, in the dark, in the silence, without any help from you at all. Somewhere in the universe right now, time is moving differently than it is moving here. Somewhere out beyond the comfortable edges of everything familiar, there are places where the fabric of space-time curves so deeply, so dramatically, so completely, that a clock placed there would tick at a rate so different from the one on your nightstand that comparing them would feel like comparing the pace of a river to the pace of a glacier. One moving with fluid, easy continuity, rushing over smooth stones and bending around fallen trees, always forward, always alive with motion. The other barely moving at all, at least to any eye that watches it for only a moment. A glacier moves, yes. It flows. It is not still. But its movement belongs to a different order of time entirely, a time scale so vast and so patient that a human lifetime pressed against it leaves no more impression than a single afternoon. That is the difference gravity can make to time. And as you rest here, as the quiet of the night deepens around you and your breathing finds its own slow, natural rhythm, I want you to feel something. Not think it. Not analyze it. Just feel it. The feeling of time being something other than what you have always assumed it to be. Because from the moment we are born, we are taught, not in words exactly, but in the deep wordless grammar of daily experience, that time is simply there. That it flows at one speed in one direction, and that this is simply the nature of things, as unchallengeable as the color of the sky or the coldness of deep water. But the universe has been quietly disagreeing with that assumption for as long as it has existed. The universe has always known that time is flexible, that it bends, that it yields, that it responds to the physical conditions around it the way that silk responds to weight, the way that sound responds to the medium it travels through, the way that light itself bends when it passes close enough to something sufficiently massive. The universe has always known this. It simply waited for a mind quiet enough and brave enough and strange enough to look at the mathematics and believe what the mathematics was saying. Einstein believed it. And in believing it, he changed everything. But here is something worth sitting with for a moment. Einstein did not discover time dilation by building a machine or running a laboratory experiment. He discovered it by thinking. By sitting quietly with the deep logic of the universe and following it wherever it led, even when it led somewhere that felt impossible, even when it led somewhere that contradicted everything the educated world of his era held to be obvious and settled and beyond question. He trusted the equations. He trusted the internal consistency of the mathematics. And the mathematics told him that time was not absolute. That two people moving at different speeds, or existing at different depths in a gravitational field, would experience the passage of time differently. He published his special theory of relativity in 1905. He was 26 years old. And with that publication, without a single experiment, without a single physical demonstration, using only thought and mathematics and a particular quality of intellectual courage that feels almost meditative in its depth and stillness, he rewrote the human understanding of reality. 10 years later, in 1915, he extended his work into the general theory of relativity, which brought gravity fully into the picture and gave us the curving, breathing, responsive image of space-time that we have been slowly exploring tonight. And the predictions that followed from that theory, predictions about the bending of light around massive objects, about the precession of Mercury's orbit, about the very structure of the cosmos itself, were confirmed one by one, decade by decade, with an elegance and a precision that continues to astonish physicists to this day. In 2015, exactly 100 years after Einstein published his general theory, scientists detected gravitational waves for the first time. Ripples in the fabric of space-time itself, generated by two black holes spiraling toward each other and merging in an event of almost incomprehensible violence and beauty, more than 1 billion light-years away. Those ripples traveled across the universe for 1 billion years, crossing distances so vast that the mind simply releases its grip trying to hold them, and arrived at Earth as a distortion in spacetime so small that it was measured in fractions of the diameter of a single proton. And yet we felt it. We built instruments sensitive enough to feel it. We listened for it and we heard it, and in hearing it we confirmed once again that Einstein's vision of a flexible, responsive, curving universe was not just beautiful. It was true. Breathe that in now. Let it move through you slowly. A ripple that traveled for 1 billion years. A distortion in the very fabric of space and time, born from the collision of two black holes when the Earth did not yet exist in anything like its current form, arriving here quietly, barely perceptibly, like the last echo of a sound made before memory began. And we were here to receive it. Small and brief and wondering as we are, we were here, and we listened, and the universe spoke. This is the context in which time dilation lives. Not as an abstract curiosity, not as a footnote in a physics textbook, but as a living, demonstrated, continuously confirmed feature of the universe we actually inhabit. The universe where you are resting right now. The universe that holds this planet and this night and this particular moment of stillness with the same quiet, curving, patient gravity that bends the path of light around a distant star. And when we begin to think about what time dilation means not just for clocks on airplanes or signals from satellites, but for the possibility of human journeys through deep space, for the extraordinary and genuine scientific possibility that a person could travel far enough and fast enough and return to find that centuries had passed in their absence, then we begin to approach something that feels less like physics and more like myth. Something that belongs to the ancient human tradition of stories told around fires, of heroes who wandered into enchanted forests and returned to find their children grown old, of sailors who disappeared into uncharted oceans and came back to shores that no longer remembered their names. And yet, this is not myth. This is mathematics. This is the quiet, irrefutable language that the universe uses to describe itself, and it says, without metaphor, without embellishment, that time is not a river flowing at the same rate for every stone upon its bed. Time bends. Time stretches. Time moves differently depending on where you are and how fast you are moving through the fabric of space itself. Let that settle for a moment. There is no need to rush toward understanding. Understanding, like sleep, arrives most completely when you stop reaching for it and simply allow the darkness to hold you. So let us stay here, in the space between equations and dreams, and walk slowly toward what it would actually mean for a human being to travel fast enough and far enough to return and find centuries dissolved in their absence. The first thing to understand is that such a journey is not a fantasy invented by science fiction writers hungry for drama. The physics that permits it is the same physics that was verified in 1971 when Joseph Haffel and Richard Keating placed atomic clocks aboard commercial airplanes and measured the precise, tiny, real difference in elapsed time when those clocks returned to the ground. The same physics that governs every signal correction made by the GPS satellites orbiting quietly above you right now as you rest. The same physics that has been tested and confirmed and reconfirmed through decades of observation and experiment with a consistency that leaves no serious scientific room for doubt. The framework is real. The effect is real. What remains is simply the question of scale. Of what happens when you take that real and verified effect and extend it, not across the modest velocities of aircraft or satellites, but across velocities that approach something close to the speed of light itself. The speed of light in a vacuum is approximately 299,792 kilometers per second. It is the universe's absolute speed limit. Nothing with mass can reach it. But nothing in the laws of physics forbids a sufficiently advanced spacecraft from approaching it, from traveling at, say, 90% of light speed, or 99%, or 99.9%. And as velocity climbs toward that unreachable ceiling, the effect of time dilation does not grow in a gentle linear fashion. It grows in a curve that steepens dramatically the closer you approach the limit. It accelerates. It compounds. It becomes, at the highest velocities, almost incomprehensible in its magnitude. At 90% of the speed of light, time aboard a moving vessel passes at roughly 44% of the rate it passes for someone who remains stationary. This means that for every 10 years experienced by the traveler, nearly 23 years would pass on Earth. Already, a significant divergence. Already, a world that would have changed meaningfully in the traveler's absence. Children older than expected. Technologies shifted. Political maps redrawn in ways that would require quiet explanation upon return. But at 99% of light speed, the factor deepens. For every year the traveler experiences, roughly 7 years pass for those left behind. And at 99.9%, that ratio approaches 22 to 1. At 99.99%, it climbs toward 70. And the mathematics does not stop there. It keeps climbing, theoretically, toward infinity, as velocity approaches the absolute limit it can never quite touch. What this means, in the most human terms possible, is that a journey which feels to the traveler like a few years of shipboard life, of waking and sleeping and breathing recycled air and watching stars shift slowly in observation windows, could correspond to something vastly longer on the planet of origin. Decades, generations, centuries, not because of any trick or illusion. Not because time moved strangely for one person but normally for another in some subjective or psychological sense. But because time itself, the actual measurable passage of physical duration, elapsed at genuinely different rates in genuinely different reference frames. The traveler would return younger, biologically and chronologically, than the civilization they had left. They would step from their ship onto a world that had continued turning without them for far longer than they had been alive. This is the effect that the title of this journey gestures toward. The strange effect. The one that makes the phrase skipping centuries not a poetic exaggeration, but a description of something that the laws of physics, as best we currently understand them, do not prohibit. And there is something profound in that. Something that asks us to sit very quietly with the realization that the universe we live in, the same universe containing this room and this night and the slow rise and fall of your breathing, is one in which the passage of time is not guaranteed to be shared equally between all living things. Consider, for a moment, what it would feel like to be that traveler. Not the physics of it, not the equations, but the texture of it. The long, quiet hours aboard a vessel moving through a darkness so vast and so complete that the stars themselves would barely seem to shift position across months of travel. The strange intimacy of a small crew, or perhaps the solitude of a single mind, held inside a moving point of light against the background of a universe that contains more stars than there are grains of sand on every beach and desert on Earth combined. The nearest star system to our own, Alpha Centauri, sits approximately 4.37 light-years from the Sun, a distance so large that even light, traveling at its absolute maximum, requires more than 4 years to cross it. And yet, at sufficiently high velocities, the traveler's experience of that crossing would be compressed. Time aboard the vessel would tick more slowly. The journey that takes light 4 years to complete might feel, to the traveler accelerating close to that same speed, like something considerably shorter. And beyond Alpha Centauri, deeper into the galaxy, the distances become numbers that the human mind was not originally built to hold. Not because we lack the intelligence to understand them intellectually, but because we evolved on a single small world where the farthest horizon was always something a pair of legs could eventually reach. Where distance meant days of walking, or weeks of sailing, or months of crossing a continent on horseback. Where the scale of the universe was simply not something our nervous systems needed to metabolize in order to survive. And so when we encounter these numbers now, in the quiet of an evening, in the slow drift toward sleep, we encounter them not with our muscles or our instincts, but with something deeper and softer. With a part of the mind that does not calculate so much as it simply opens. That receives the enormity the way a still lake receives the reflection of a sky it could never contain. The Milky Way galaxy, the one that holds our sun and all its planets and every living thing we have ever known or imagined, spans approximately 100,000 light-years from edge to edge. 100,000 years of light travel. 100,000 years of photons streaming through vacuum, touching nothing, passing through clouds of gas and dust and the gravitational shadows of dead stars, just across the width of the place we call home. And our galaxy is one of an estimated 2 trillion galaxies in the observable universe. 2 trillion islands of stars, each containing hundreds of billions of suns, each separated from its nearest neighbor by distances measured not in light-years but in millions of light-years. The observable universe itself stretches approximately 93 billion light-years across. A number so large it does not produce awe so much as a particular quality of silence. The kind of silence that comes after a very long, very deep breath. And into this silence, we bring the traveler again. the human being aboard the vessel moving at some extraordinary fraction of the speed of light. Moving not to Alpha Centauri now, but deeper, across greater distances, towards something further in the dark. And as the velocity climbs and the time dilation factor deepens, something genuinely strange begins to happen to the relationship between the traveler's experienced duration and the duration accumulating back on the world of their origin. A journey to the center of the Milky Way, roughly 26,000 light-years away, would take light itself 26,000 years to complete. But a traveler moving at a sufficient fraction of light speed, close enough to the absolute limit to produce a dilation factor in the dozens or hundreds, could experience that journey in something far more compressed. Not 26,000 years of personal time. Not thousands. Not hundreds. But potentially decades. Or less. The arithmetic is precise and it does not flinch. The closer to the speed of light you travel, the more dramatically the universe contracts its demands on your personal clock. The ship moves. The stars shift. The destination approaches. And aboard the vessel, time passes at its own quiet rate, slower than the rate accumulating in the world left behind, and the traveler ages gently through weeks or months or years while the civilization of their origin ages through centuries. This is not magic. There is no spell being cast, no loophole being exploited in the fabric of reality. It is simply reality, behaving according to its own deepest nature. A nature that does not privilege any single clock above any other. That does not insist that your heartbeat and the heartbeat of a distant star must pulse in the same rhythm. The universe has no central timekeeper. No master clock against which all others are measured and corrected. There is only the local rate of time, experienced by each observer according to their velocity and their position in a gravitational field, and the relationship between those local rates, described with complete precision by equations that have never, in the entire history of their testing, been found to be wrong. And there is something in that absence of a master clock, something in that radical democracy of experience time, that feels quietly profound when held in the mind at rest. We tend to imagine time as something universal, something shared. We imagine that the moment you are living right now, this breath, this heartbeat, this particular instant of awareness balanced between wakefulness and sleep, is somehow simultaneous with every other moment happening everywhere else. That there is a single now that stretches across the cosmos like a flat, invisible plane, touching every star and every sleeping creature and every drifting asteroid at once. But relativity dismantles that assumption gently and completely. There is no universal now. There are only local nows, each one valid, each one real, each one flowing at its own rate depending on the conditions of its existence. What you experience as this moment is genuinely this moment for you. And simultaneously, somewhere else in the universe, something is experiencing its own moment, and those two moments cannot be placed into a single agreed-upon sequence without choosing a reference frame, without deciding, somewhat arbitrarily, whose clock we trust to define the order of things. This is not a philosophical puzzle dressed in the language of science. It is what the science actually says. It is what the experiments actually confirm. And it rests beneath every conversation about time dilation, beneath every thought about the traveling human and the centuries that pass in their absence, as a kind of foundation that is simultaneously the most solid and the most unsettling ground imaginable. Solid because it is verified. Unsettling because it suggests that the universe is far stranger and far more generous with its strangeness than the ordinary hours of a human life typically reveal. We move too slowly in our daily existence to feel the divergence. We live too close to one another, on the surface of a single planet, within a gravitational field that curves time at very nearly the same rate for all of us, to notice that our clocks are not perfectly synchronized. The differences at human scales and human speeds are real but vanishingly small. A billionth of a second here. A fraction of a microsecond there. Enough to matter to an atomic clock. Not enough to matter to a life lived between breakfast and sleep. And so we carry through our days the comfortable illusion that time is one thing, shared equally, moving at the same rate for everyone who has ever drawn breath beneath this sky. But the universe does not share that illusion. The universe has never shared it. It was always this way, even before we had the mathematics to see it. Even before Einstein sat quietly with his thoughts and began to ask what it would mean to ride alongside a beam of light. Even before the first atomic clock was built, or the first satellite launched, or the first airplane carried a cesium oscillator across a continent to prove that duration is not fixed. The universe was always conducting this silent, vast, unannounced experiment in relative time. And we were always inside it. Living inside it, breathing inside it, sleeping inside it, as you are doing now, or nearly doing, your body settling into stillness while the planet beneath you curves through space at roughly 30 kilometers per second in its orbit around the Sun itself moving at approximately 230 kilometers per second around the center of the galaxy drifting at over 600 kilometers per second relative to the cosmic microwave background. You are, in this moment of apparent rest, moving through space at speeds that would have seemed incomprehensible to every human generation before the last few centuries. And even at those speeds, the time dilation you experience relative to a truly stationary observer, if such a thing could exist, is real, measurable, confirmed. What changes, when we think about the deep space traveler, is only the magnitude. The same effect, stretched by enormously higher velocities into consequences that span not microseconds but decades, not fractions of a heartbeat but entire historical eras. And the question that begins to surface, slowly, the way a question surfaces in the mind at the edge of sleep, is not whether this is possible. The physics has already answered that. The question is what it would mean, what it would feel like from the inside. What the shape of that experience would be, for a conscious human mind moving through the dark at a speed that unmoors it gently but completely from the timeline of everyone it has ever loved. Imagine the departure, the last sight of a blue world receding in the observation window. The way its light would diminish not dramatically but gradually, the way all true distances reveal themselves, slowly, over time. The people on that surface continuing their lives, their days cycling through the ordinary rhythms of morning and evening, of seasons and years, while the vessel accelerates, while the distance grows, while the velocity climbs toward something that has no precedent in the entire history of human travel. There would be a strangeness to the early hours of such a journey that has nothing to do with physics and everything to do with the particular human ache of separation. The knowledge that time is already beginning to diverge. That every hour passing aboard the ship corresponds to slightly more than an hour passing below. That the gap, invisible at first, is already opening like a very slow tide withdrawing from a shore. And then the weeks. And then the months. And the gap widening. Accelerating as the vessel accelerates. The dilation factor deepening. Until the correspondence between shipboard time and the time of the origin world becomes something that cannot be casually maintained in the mind. Something that requires a kind of deliberate, almost meditative acceptance. The traveler would know, in an abstract and mathematical sense, that years are accumulating behind them. That people they knew are older. That some of them, depending on the length of the journey, are gone. That the world they left is not precisely the world to which they will return. This is not speculation. This is what the equations describe. And the equations are not in the habit of softening their implications for emotional convenience. There is a kind of loneliness in that knowledge that belongs to no previous human experience. Not the loneliness of distance, exactly, though the distances would be beyond any prior human reckoning. Not the loneliness of isolation, though isolation aboard a vessel crossing the space between stars would be its own vast and quiet thing. But the loneliness of temporal displacement, of knowing that the river of shared time, the one that has always connected every human being to every other human being through the common experience of hours and days and seasons, has divided. That you are in one current and everyone you love is in another, and the currents are moving at different speeds through the same landscape. That when they meet again, if they meet again, they will not meet at the same point downstream. They will meet across a distance measured not in kilometers but in years, in decades, in the quiet accumulation of everything that happens to a world while one of its children is away. And there is no remedy for this. No communication that closes the gap. No message that travels faster than light to carry news of what has been missed, because nothing travels faster than light. That is not a technological limitation waiting to be overcome by a sufficiently clever civilization. It is a boundary written into the structure of reality itself, as fundamental as the existence of space or the direction of time. And so the traveler moves through the dark in a kind of beautiful and terrible solitude that no word in any human language was coined to describe, because no human being has yet lived it. We have only the mathematics to point toward it. And the mathematics points with great precision and no comfort whatsoever. But there is something else the mathematics offers, alongside its unflinching honesty about separation. It offers the journey itself. The actual experience of moving through space at velocities that compress distance into something traversable within a human lifetime. And that experience, strange and isolating as it would be in certain registers, would also be something else entirely. Something that resists easy categorization. Something that might only be approached by holding it very gently in the mind, the way you hold a thought at the very edge of sleep, not gripping it, not analyzing it, but simply allowing it to be present. Consider what the traveler would see, not with instruments or calculations, but with their eyes. At velocities approaching the speed of light, the universe does not look the way it looks from the surface of a slowly orbiting planet. The phenomenon known as aberration causes the apparent positions of stars to shift toward the direction of travel. The sky ahead brightens and compresses, stars crowding toward a central point as though the universe is gathering itself to meet you. Colors shift as well, a consequence of the Doppler effect applied to light itself, the stars ahead bluing as their wavelengths compress toward the shorter end of the spectrum, the stars behind reddening as their wavelengths stretch. And at extreme velocities, the effect deepens further, into something called relativistic beaming, where the light of the entire visible universe appears to concentrate into a shrinking circle of brilliance directly ahead, while the darkness behind becomes nearly absolute. You would be traveling, in a sense, into a tunnel of compressed starlight, into a brightness gathered from across the whole of the observable cosmos, focused by your own velocity into a single luminous point drawing you forward through the dark. There are no photographs of this. No human being has traveled fast enough to witness it directly. But the physics is understood well enough that we can describe it with confidence, the way we can describe the surface of a distant planet using only the light it reflects and the mathematics of how light behaves. The universe, at those velocities, would be visually transformed. Not distorted in a chaotic or random way, but transformed according to precise and elegant rules. The same rules that govern the bending of light around a massive star, that determine the frequency of radiation emitted by a hydrogen atom, that describe the expansion of space itself across cosmic scales. Everything obeying the same deep grammar. Everything participating in the same underlying order that the universe has maintained, without interruption or exception, since the first fraction of a second after its own beginning. And aboard the vessel, moving through that compressed and beaming light, the traveler's own body would continue its quiet biological rhythms. The heart beating, the lungs expanding, the cells dividing and repairing and eventually aging, slowly, at the rate that biology has always aged, unaffected in its own local frame by what the clocks on distant planets are doing. This is perhaps the most intimate and the most remarkable aspect of time dilation when considered from the inside. The traveler does not feel slow. They do not experience their own time as stretched or compressed or unusual in any way. Their coffee, if they had coffee, would cool at the same rate it always cools. Their wounds, if they had wounds, would heal across the same span of days they have always healed. Their thoughts would arrive and dissolve with the same texture of experienced duration that thoughts have always had. Everything local, everything immediate, everything belonging to the small warm sphere of their own embodied existence would feel entirely, unremarkably normal. It is only in relation to something else, something outside the vessel, something anchored in a different reference frame, that the divergence becomes visible. Time dilation is, in this sense, not an experience but a relationship. Not something you feel but something that becomes apparent only when two clocks are brought back together and compared. Only when the traveler returns, or sends a signal, or in some way re-establishes contact with the frame they left, does the accumulated difference reveal itself. Quietly. Completely. Without drama and without apology. This many years have passed here. This many years have passed there. The difference between those two numbers is not an error. It is not a malfunction of either clock. It is the universe, faithfully and without exception, honoring the geometry of its own spacetime. Honoring the agreement it made with itself at the very beginning, before there were any clocks to measure it, or any minds to wonder at what the measurements revealed. Before there were any travelers to carry the strange and weightless cargo of slower time. The strange and weightless cargo of a clock that disagreed with the world it returned to. And this cargo, invisible, massless, carrying no scent and casting no shadow, may one day be the most important thing a human being ever learns to pack. Imagine, if you are still awake enough to imagine, a vessel. Not the cold mechanical shell of early science fiction, not the roaring chemical fire of the rockets we have already built and launched and watched disappear into the dark above our atmosphere. Something quieter. Something that has solved, in whatever distant century we are asking you to picture, the problem of sustained velocity. A vessel that moves at some meaningful fraction of the speed of light. Not all of it. Not yet. Perhaps a tenth. Perhaps a quarter. Perhaps, in the most generous version of this thought experiment, 9/10 of the whole impossible number. The exact fraction matters less than the principle it carries. The principle being this, that the crew inside that vessel, breathing recycled air and watching stars shift slowly in their positions through reinforced observation windows, would be aging at a rate that the Earth below, or behind, or impossibly far away in some direction that no longer maps cleanly onto human intuition, would not recognize as normal. They would feel normal. That is the first and perhaps most important thing to understand. There is no sensation of slowness. No feeling of time thickening around you like cooling amber. The coffee in the cup cools at its usual rate. The heart beats with its familiar rhythm. The mind drifts toward sleep with the same gentle insistence it has always had. Everything internal, everything enclosed within the bubble of that moving reference frame, proceeds according to its own internal logic, perfectly consistent, perfectly unremarkable. It is only the outside that changes. It is only the relationship between the moving clock and the stationary one that accumulates its quiet, mathematical difference. And so a journey that feels, to the crew, like 2 years, might correspond to something else entirely for the civilization that launched them. Depending on the velocity. Depending on the curve of space-time that velocity carves. 10 years might pass on the surface of the Earth while the crew experiences 20 years. 40. In the most extreme cases, the ones that live at the edge of what the equations permit, the ones that approach the asymptote of light speed without ever quite touching it, the ratio becomes almost theological in its strangeness. Centuries outside, a human lifetime within. This is not a metaphor. It is not a poetic license taken with the facts to make them feel more interesting than they are. The facts, in this case, require no such assistance. They are strange enough without decoration. Time dilation at relativistic velocities has been confirmed not in thought experiments alone but in real measurements, made with real instruments, in the real world we all share. Atomic clocks flown on aircraft have returned to the ground running slightly behind the clocks left at the surface. Satellites in orbit, moving fast enough and high enough above Earth's gravity well, require constant relativistic corrections to maintain the accuracy that makes navigation possible. Without those corrections, GPS systems would drift by several kilometers per day. Every time you ask a device to tell you where you are, the answer it gives you has been quietly adjusted to account for the fact that time does not pass the same way at altitude as it does at sea level. The universe insists on this. The equations insist. And so, with the pragmatic grace of engineers who have made peace with strangeness, we simply build the correction in and go about our lives. But aircraft corrections are measured in nanoseconds. Satellite corrections in microseconds. The effects are real, but they are small enough to be invisible to any biological clock, small enough to require instruments of extraordinary precision to detect. To make the effect large enough to matter in human terms, large enough to feel, large enough to return home a recognizable person to a world full of strangers, you would need velocities that our current civilization cannot produce and may not produce for centuries. Which is, of course, the point. Which is precisely where the strangeness opens up into something that feels less like physics and more like myth. Consider the numbers simply and without rushing them. A vessel traveling at 90% of the speed of light experiences time at roughly 43% of the rate experienced by a stationary observer. For every 10 years that pass outside, approximately 4 years and 4 months pass inside. A journey of 40 light-years to a nearby star system, to one of the candidates that astronomy has begun to identify with hopeful attention, would take the crew something closer to 17 years of felt time, while 44 years accumulated on the planet that watched them leave. A generation on Earth, passing like a long and quiet season on the ship. And if the vessel could push further, could press closer to the limiting velocity, the compression deepens. At 99% of light speed, time aboard slows to roughly 14% of the outside rate. At 99.9%, it contracts to less than 5, that the traveler becomes, in a very precise and technical sense, a visitor from a different temporal position. Not the past, not the future, but something that sits outside the normal accounting of both. A traveler who left in one era and returned in another, carrying within their body the evidence of a path through space-time that no one else on Earth had taken. Carrying the lived experience of a shorter journey through a universe that had, in their absence, continued its own patient unfolding without waiting for them to catch up. And there is something in this that resists easy categorization. Something that sits at the edge of what language was built to hold. Because we have words for travelers who return changed. We have stories about them, ancient ones, told around fires that have long since gone cold. The hero who descends and comes back older in spirit if not in body. The wanderer who finds the village transformed when they finally walk back through its gate. But those stories assumed a shared time. They assumed that however far the traveler had gone, the clock above the mantle and the clock in the traveler's chest had been keeping the same count. That the years felt long because they were long, for everyone equally. What relativity introduces is something those old stories had no framework for. The possibility that the years were not equal. That the traveler and the village were not separated only by distance but by time itself, measured differently, accumulated differently, spent at different rates like two people drawing from the same well but through pipes of unequal diameter. The wanderer returns not just to a changed world, but to a world that has changed more than they have. A world that has had more time to change. And the wanderer, standing at the gate, is younger than they should be. Younger than the calendar insists they ought to be. Younger, in a sense that is not metaphorical but physical, cellular, atomic. This is the twin paradox, though calling it a paradox gives it more confusion than it deserves. It is not truly paradoxical. It only appears so when you consider it incompletely. When you ask only the first half of the question. If motion is relative, you might wonder, then who is to say which twin moved and which stayed still? Could the traveling twin not claim, from within their own reference frame, that it was the Earth that moved away and returned? Could they not, by that reasoning, expect to find their sibling younger upon reunion rather than older? The answer is no. And the reason is subtle but not mysterious. The two twins do not have equivalent experiences. One of them remained in a single inertial frame, moving through time at a steady and uninterrupted rate. The other accelerated, turned around, decelerated, accelerated again. It is in those moments of acceleration, those changes in velocity that are not relative but absolute, felt as pressure, felt as weight, felt as the body being pushed into the seat of the vessel, that the symmetry between the two frames breaks. That the two paths through space-time diverge in a way that is not a matter of perspective but of geometry. The traveling twin traces a shorter path through the four-dimensional fabric. Not shorter in space, longer in space, but shorter in time. And when the two paths rejoin at the same point, the difference in their lengths is written in the difference between the ages of the two people standing face to face. The universe keeps its accounts carefully. Every acceleration is noted. Every curve in the path through spacetime is factored in. And when the journey is complete, the total is presented without negotiation. This is how much time passed for you. This is how much time passed for them. The difference is not a rounding error. It is the ledger of spacetime, balanced to the last decimal place. And so we return, slowly, to the question of centuries. To the idea with which this long and unhurried exploration began. The idea that time, under the right conditions, could be made to move at something other than the rate we have always taken for granted. That a human life, finite and tender and irreplaceable, could be stretched across a far greater span of external history than biology alone would suggest. That someone born in one century could, without any violation of natural law, without any miracle or magic or suspension of the rules that govern everything else, step out of a vessel and find themselves standing in another. Not through sleep. Not through the cold suspension of biological process that science fiction has always offered as the gentler alternative, but through motion itself. Through the simple, profound, geometrically consequential act of moving very fast for a very long time and then stopping. The stars make this feel almost reasonable, if you let yourself sit with it long enough. The stars, after all, are already doing something similar to our perception of them. When you look at the night sky, you are not seeing the sky as it is. You are seeing it as it was. The light arriving in your eyes left its source years ago, decades ago, in some cases millions of years ago, and has been traveling ever since, carrying its information faithfully across a distance so large that the numbers require a different vocabulary than the one we use for ordinary things. Light from the moon left its surface a little over a second before it reached you. Light from the sun, 8 minutes. Light from the nearest star beyond our own, more than 4 years. And from the faint smudges at the edge of what our instruments can detect, the light arriving tonight departed before. The Earth existed, before the sun had condensed from its cloud of gas and dust. Before the solar system had taken its shape, before there were oceans to reflect this light back upward, before there was any surface at all for it to fall upon. That light has been traveling since a time so remote that the planet you are lying on had not yet been assembled from the raw material of an earlier star's death. And yet here it is, arriving now, touching your eyes with information that is older than the ground beneath you. There is something in this that asks to be felt rather than merely understood. Something that does not resolve into clarity the way a mathematical proof resolves, but instead opens, slowly, like a room you did not know was there, behind a door you had walked past every day without trying the handle. The universe is not presenting itself to you as it is. It is presenting itself to you as it was, at varying distances, at varying removes, so that the sky above you at any given moment is not a single snapshot but a kind of deep archive, a layered record of different moments stacked together into the illusion of a simultaneous scene. The star you are looking at may no longer exist. It may have exhausted its fuel and collapsed inward in a final, spectacular gravitational surrender centuries before the light now reaching your eyes ever left its surface. You are seeing a ghost. Not in any supernatural sense, but in the most literal physical sense available. You are receiving a signal from something that sent it long before you were born and may have ceased to exist long before you thought to look up. And this, too, is a kind of time travel. Passive. Involuntary. Built into the very act of perception. Every time you look at the night sky, you are reaching backward through time with your eyes, pulling in light that carries the past inside it like a message sealed in the moment it was sent and only now delivered. The universe has been writing you letters for billions of years, and they are all arriving at once, each from a different era, each from a different remove, each a small and luminous testament to the fact that time and space are not the separate, independent things our daily experience suggests. They are woven together. They respond to each other. A change in one produces a change in the other, quietly, consistently, in accordance with equations that were not invented but discovered, not imposed upon the universe but read from it, the way you might read the grain of a very old and patient wood. And so when we speak of traveling through time in the relativistic sense, we are not speaking of something alien to the universe's nature. We are speaking of an extension of something it has always been doing. The universe has always been mixing space and time, always been allowing different regions and different velocities to accumulate their histories at different rates. Life and consciousness, and the fragile human desire to endure, are simply late arrivals to a process that was already ancient when the first star ignited. We are asking to participate more deliberately in something that has been happening around us and to us since the beginning. The light from a distant galaxy arrives here, having traveled for so long that the galaxy itself has moved. The universe has expanded in the time the light was in transit, and the source is now far further away than the distance the light actually crossed. Space itself stretched while the light was moving through it. And the light, faithful traveler, arrived anyway, carrying its cargo of old information into the instruments of astronomers who spend their lives learning to read the deep past written in wavelengths of radiation that human eyes alone were never built to see. This is the context in which time dilation lives. Not as an anomaly, not as a footnote, but as one expression of a universe that has never treated time the way we assumed it did when we were young, and the clocks on the wall all agreed with each other, and there was no particular reason to suspect that they might not always do so. The clocks agreed because they were close together and moving at similar speeds and sitting in similar gravitational fields. Their agreement was not a law. It was a coincidence of circumstance. A local and temporary convergence that felt permanent because we had no instruments sensitive enough to detect the divergence and no velocities available to us large enough to make the divergence visible to the naked eye. We lived, for most of human history, inside a small region of spacetime where the effects were so minute as to be invisible, where you could be forgiven for assuming that time was a river and that the river moved at the same speed everywhere and that all you had to do was float and you would arrive at the future at the same moment as everyone else floating alongside you, where the idea that someone might arrive later or earlier in any meaningful sense, would have sounded like the kind of story told to children to help them fall asleep, rather than the kind of story told by physicists to help everyone understand what the universe is actually made of. What it is actually doing, beneath the surface of the ordinary, beneath the calm and unremarkable face it presents to those of us who have never moved fast enough or fallen deep enough into a gravity well to feel the fabric shift beneath us. The universe has a texture that daily life does not reveal, a depth that only becomes visible at the edges of experience, at the extremes of velocity and mass and distance, where the comfortable assumptions begin to loosen and the stranger truth underneath starts to show through like a different color of paint beneath the one applied on top. And gravity is part of this. Gravity, which we have not spoken of as much as we might, is the other hand that shapes the flow of time. Not just velocity, not just motion through space, but the curvature of space-time itself, produced by the presence of mass, pulling at the geometry of the universe the way a heavy object placed on a stretched fabric pulls the fabric down around it, creating a depression, a well, a slope along which other objects naturally tend to fall without any force pushing them. What we call the force of gravity is, in Einstein's description, not a force at all. It is the natural consequence of moving through curved spacetime. It is what straight-line motion looks like when the space you are moving through is not flat. And time, in the presence of mass, slows. This is gravitational time dilation, distinct from the velocity-based variety but arising from the same deep source, the same fundamental truth about the relationship between geometry and the rate at which time passes. A clock placed close to a massive object, close to the dense gravitational field that object produces, will tick more slowly than a clock placed far from it. Not because the clock is broken. Not because the gravitational field interferes with the clock's mechanism in any direct or mechanical sense. But because time itself is passing more slowly there. Because the geometry of spacetime near a massive object is different from the geometry far from it, and that difference in geometry is a difference in the rate of time. This has been measured. Here, on this small and unhurried planet, with instruments that required extraordinary care to build and extraordinary patience to read. Clocks at sea level run slightly slower than clocks at the top of a mountain, because sea level is closer to the center of Earth's mass, deeper in the gravitational well, sitting in a region of more strongly curved spacetime. The difference is small. Everything about gravity on Earth is small, relative to the scales on which these effects become dramatic. But the difference is real, and it has been confirmed, and it fits the equations with a precision that leaves no room for doubt. Now carry that principle to larger scales, to objects of greater mass, to the collapsed remnants of stars that burned for millions of years and then ran out of fuel and fell inward, compressing their remaining mass into a volume so small and a density so extreme that the curvature of spacetime around them becomes a different thing entirely. A neutron star, the compressed core of a dead sun, packs more mass than our entire star into a sphere perhaps 20 kilometers across. The gravitational field at its surface is so intense that a clock placed there would run at a measurably different rate than a clock floating far above it. Time, near a neutron star, does not pass the way it passes here. It passes more slowly, more heavily, as if the weight of all that compressed matter presses not just on space but on time itself, thickening it, deepening it, making each second a longer and more laborious thing. And beyond neutron stars, further along the same continuum of compression and curvature, there are objects for which we have a name but not yet a complete understanding. Objects where the curvature of spacetime becomes so extreme that it closes in on itself, where the escape velocity exceeds the speed of light, where not even the fastest thing in the universe can move quickly enough to climb back out of the well. We call them black holes, which is a name that sounds final and dramatic and perhaps gives the impression that we understand them more completely than we do. We understand their exteriors well. We understand the mathematics that describes the geometry of spacetime around them, the elegant and austere equations that predict how matter and light and time behave in their vicinity. What happens beyond the boundary, inside the region from which no signal can return, remains genuinely unknown. The equations suggest answers, but the answers exceed our ability to test them, and in science, an answer that cannot be tested is held loosely, like something valuable that you carry in an open hand rather than a closed fist. But what we do know, what the equations and the observations and the careful accumulation of evidence all agree upon, is that time near a black hole behaves in ways that stretch the imagination without quite breaking it. That a clock falling toward the event horizon, the boundary beyond which return becomes impossible, would appear to an outside observer to slow, to approach stillness, to asymptotically near the boundary without ever quite crossing it, from the outside perspective, while from the perspective of the clock itself, from inside the falling frame, the crossing happens in finite time. The crossing happens, and the clock continues, and the universe does not pause to acknowledge the threshold that has been passed. This is one of the more disorienting features of relativistic physics, and perhaps one of the most important to sit with quietly before moving on. That two observers, both equally real, both equally valid, can witness the same event and come away with accounts that seem irreconcilable. The observer at a safe distance watches the falling clock slow and redden and dim, the light stretching as it climbs out of the deepening gravitational well, the clock's hands appearing to approach but never quite reach the moment of crossing. And the observer riding with the clock, the one falling freely through the curved geometry of spacetime, feels nothing dramatic at the horizon. No wall, no warning, a threshold defined entirely by what is now impossible, not by what can be felt or seen or touched in the moment of passing through it. We tend to think of reality as something singular, something that one account can capture completely, if only the account is careful enough and precise enough and honest enough. But spacetime, in its actual behavior, seems to suggest otherwise. That perspective is not merely a limitation of the observer, but a genuine feature of the universe itself. That where you are, and how you are moving, and how deeply you are situated in a gravitational field, all of these shape not just how you perceive events, but when those events occur for you, in what sequence, at what rate. Time is not a river flowing at the same speed for everyone who stands beside it. It is something more like a landscape, uneven and textured, with regions of stillness and regions of rushing forward, and the path you take through it determines, in the most literal physical sense, how much of it you experience. And so when we speak of time dilation near a black hole, we are not speaking in metaphor. We are speaking about clocks. Real clocks. The kind that physicists have tested in aircraft flying at altitude, in satellites orbiting at speed, in experiments conducted carefully over decades with atomic precision. The equivalence principle, which lies at the heart of general relativity, tells us that gravity and acceleration are locally indistinguishable, that the geometry of spacetime curves wherever mass is present, and that this curvature, this warping of the fabric through which all things move, is precisely what we feel as gravitational force. And where the curvature deepens, time moves more slowly. This is not an approximation. It is not a model that works in limited circumstances. It is accurate. It has been measured. It is built into the correction algorithms of every GPS satellite currently in orbit, because without accounting for the difference in the rate of time between the surface of the Earth and the altitude of those satellites, the positioning errors would accumulate by kilometers each day. The mathematics of curved spacetime is not theoretical luxury. It is engineering necessity. But GPS satellites are far from black holes, and the time differences they experience, though real and measurable and practically significant, are modest by the standards of the universe's more extreme environments. To find the places where time dilation becomes something that might genuinely reorder a human life, something that might send a traveler forward through centuries rather than microseconds, we have to move closer to those regions where the curvature of spacetime becomes not a gentle slope but something vertiginous and steep. And the closest such environment we can describe with mathematical confidence, the one that our equations reach most cleanly, most precisely, is the vicinity of a black hole. Specifically, the region just outside the event horizon, where the geometry has become so extreme that to hover in place, to maintain a fixed position against the inward pull of curvature, would require acceleration so vast it lies entirely beyond human technology. But to orbit there, to move in a close, tight path around the boundary, requires only that you be falling freely in a very specific way. And a traveler doing so, circling in the deep gravity of a massive black hole, would find that when they returned to the wider universe, to the ships and stations and people they had left behind, those people would be older. Much older. The travelers themselves, by their own biology, by their own internal clocks, by the accumulation of heartbeats and breaths and cellular divisions that constitute a living body's experience of duration, would have aged only slightly. But the universe outside would have moved on. This is the scenario that physicists describe when they speak of gravitational time dilation as a mechanism not just for slowing time but for moving through it asymmetrically. Not time travel in the popular sense, not the reversal of sequence, not the ability to reach back and alter what has passed, but something perhaps more strange, and in certain moods more melancholy. The ability to arrive in a future that belongs to other people. To step back into a world that has continued without you, that has grown older in your absence, that has accumulated its changes and its losses and its developments while you were moving through a slower region of space-time, while your clock was ticking at a rate that the universe, from its wider vantage, experienced as glacially, almost impossibly slow. There is a particular feeling that attaches to this idea when you hold it long enough. A feeling not quite like any other in the catalogue of scientific wonder, because it carries within it something that touches not just the intellect but the part of you that understands, quietly and without needing it explained, what it means to be left behind. Or to leave. Because the asymmetry cuts in both directions, depending on which side of the departure you occupy. The traveler who falls into deep gravitational time and returns to find centuries elapsed is not the one who has lost the most, not in the conventional sense of loss, not in the sense of years subtracted from a life. They have lived their moments fully. They have breathed and thought and moved through their experience at the pace their body recognized as normal. It is the ones who remained, the ones who continued at the ordinary rate, who accumulated the weight of all that intervening time. And yet the traveler carries something else. A discontinuity. A gap in the shared story of their world that no amount of reading or recounting can fully bridge. They return to a future that has no memory of their presence in its making. This quality, this particular texture of gravitational time dilation, is what separates it most completely from other forms of strangeness in physics. Quantum uncertainty is strange, but it is everywhere, affecting everything equally, and so it becomes a kind of background, something you eventually accept as the fundamental grain of reality. The expansion of the universe is strange, but it operates on scales so vast that the human mind can only gesture toward it, can only hold a symbol where direct comprehension would need to live. But gravitational time dilation is strange in a way that feels personal. It operates on bodies, on clocks, on the rate at which a heart moves through its allotted beats. It is the kind of strangeness that, if you let it settle fully into your thinking, quietly rearranges something in how you understand your own position in time. Not as a passenger moving along a fixed track, but as something more vulnerable and more singular than that. A traveler whose experience of duration is genuinely, physically shaped by where they go and how they move. And the universe, it turns out, contains places where this shaping becomes extreme enough to constitute something almost mythological in its implications. Regions where time does not merely slow but where, from certain external perspectives, it seems to approach a kind of stillness that the mind keeps wanting to call an ending, even though it is not an ending. It is something more difficult to name. A boundary condition. A place where the ordinary grammar of before and after begins to require revision. The event horizon of a sufficiently massive black hole is one such place. And there is a particular class of black holes, the ones that rotation has stretched into a specific geometry, that present an environment slightly less immediately fatal to a hypothetical traveler than the smaller, denser variety. These are called Kerr black holes, after the mathematician Roy Kerr, who in 1963 found the exact solution to Einstein's field equations for a rotating mass. What he found was not simply a scaled version of the simpler non-rotating case. Rotation changes the geometry in ways that are rich and strange and still being understood. A rotating black hole drags spacetime itself around with it, the way a spoon pulled through honey causes the honey to rotate, except that what is rotating here is not a fluid but the very medium through which all things, including light, must move. This effect is called frame dragging, and it means that near a rotating black hole, you cannot remain still relative to the distant stars no matter how hard you accelerate against the rotation. The geometry itself is moving, and you are inside it. But within this stranger geometry, within the layered structure of ergospheres and inner and outer horizons that rotating black holes possess, there are orbital paths, specific trajectories around the black hole, where a traveler could in principle survive long enough to experience the time dilation in a way that the simpler picture only gestures toward. Close orbits around massive, rapidly rotating black holes, orbits that remain outside the event horizon but deep enough within the gravitational well that the curvature is extreme, will produce time dilation factors not of seconds or minutes or hours but of years, decades, centuries. A traveler completing what felt to them like a single day of careful orbiting might return to a station positioned safely far from the black hole and find that years had passed for those who waited. The ratio between inner time and outer time grows with proximity and mass and the depth of the gravitational field. Push the numbers far enough, and that ratio becomes not poetic but literal. A week near the horizon equaling decades further out. A year of close orbital travel corresponding to centuries in the wider universe. This is the mechanism that makes black holes the only objects in the known universe that could, in principle, allow what might loosely and carefully be called a skip through time. Not a journey backward, not a reversal, but a compression. A situation in which the traveler arrives in a future they did not live through, carrying a body that has aged only slightly, entering a universe that has moved on by an amount that strains ordinary human categories. The people they knew would be gone. The institutions they recognized would have changed beyond recognition, or disappeared entirely, or evolved into forms with no direct continuity to what they remembered. The language might have shifted. The sky, from any given planet, would look nearly the same, because stars move slowly on human timescales, but nearly everything built upon the surfaces below those stars would be unrecognizable, or gone, or replaced by something that the traveler would need time to learn to read, the way you need time to learn a new alphabet before the letters stop looking like shapes and start looking like meaning. And this, perhaps, is the detail that carries the most weight when you sit with the idea long enough. Not the physics, which is extraordinary enough on its own terms, but the human texture of the arrival. The moment of return. The traveler stepping back into a universe that has continued without them, carrying memories of a world that no longer exists in the form they remember it, standing at the threshold of a future that belongs to strangers who share their history only at a distance, only in the way that we share history with people who lived centuries before us, as inheritance rather than experience. There is a word that exists in several languages for the feeling of returning to a place and finding it changed, of walking back into a landscape you knew and discovering that the knowing no longer fits the thing itself. English does not have a single clean word for this, which may say something about the English relationship to time and place, or may simply be a gap in the vocabulary that other languages happen to fill first. But the feeling itself is universal enough, recognizable enough, that most people have encountered some version of it. The childhood home that has been renovated. The neighborhood that has been rebuilt. The face of someone you loved, seen again after years apart, carrying the quiet evidence of all the time that passed without you in it. These are small versions of the same structure that gravitational time dilation makes possible at a scale the emotions have no practiced way of processing. And yet the emotions would still be there, in the traveler's body, shaped by evolution for a world where time moved at the same rate for everyone, now asked to respond to a situation that evolution never anticipated and cannot have prepared for. This is one of the reasons that thought experiments involving black holes and time dilation are not merely technical exercises. They are, in a quieter and more persistent way, experiments in what it means to be a creature that experiences time personally, internally, as a felt quality of existence, and simultaneously inhabits a universe where time is not a fixed and universal medium but something that bends and varies and moves at different rates in different places. The physics reveals something about the nature of time. But the act of imagining a human being inside that physics reveals something about the nature of us. We are, all of us, moving through time at approximately the same rate, near the surface of the same planet, within a gravitational field deep enough to produce measurable time dilation relative to orbit but shallow enough that the differences between any two people's experience durations are, over the course of a lifetime, smaller than the precision of any biological clock. We share time in a way that feels absolute because, within the narrow range of our ordinary experience, the variations are negligible. But the universe does not share our narrowness. The universe contains environments where the rate of time varies by factors that would, if experienced by a conscious being, constitute something genuinely alien to the entire framework of shared human experience. And black holes are the most extreme such environments we have been able to describe with mathematical precision and observational support. In 2019, the Event Horizon Telescope collaboration released the first image ever captured of a black hole's shadow. The black hole at the center of the galaxy Messier 87, a galaxy roughly 55 million light-years from Earth, a black hole with a mass approximately 6.5 billion times the mass of the Sun. The image was blurred by the limits of resolution achievable across interstellar distances, but the structure was unmistakable. A ring of bright emission surrounding a central darkness. The bright ring was light, bent by the extreme curvature of spacetime around the black hole, photons that had traveled paths curved almost back upon themselves by the geometry of that region, arriving at our telescopes after a journey shaped by the same mathematics that predicts the slowing of time in the black hole's vicinity. The image was not just a picture. It was confirmation. A direct visual contact with a class of object whose existence had been inferred from equations and indirect evidence for more than a century, now revealed as unambiguously real, as genuinely present in the universe, as available, in at least some limited sense, to the human eye. And at the center of our own galaxy, closer and in some ways more studied, lies another. Sagittarius A star, a black hole of approximately 4 million solar masses, its presence revealed not by imaging, initially, but by the careful tracking of stars orbiting an invisible center, stars moving in paths that only made sense if something of immense mass occupied the point around which they curved. Those stars, some of them, orbit close enough to Sagittarius A star that their velocities reach several percent of the speed of light. They experience time dilation both from their speed and from their proximity to the mass they orbit. They are clocks, moving through spacetime in a way that the physics predicts with precision, aging slightly more slowly than stars that orbit further out, accumulating their time in a field so deep that the difference, while not dramatic by the standards of the thought experiments we have been following, is real, measurable, written into the fabric of what those stars are, not as a poetic description but as a physical fact that the equations predict and that careful observation confirms. There is something quietly astonishing about this, if you let yourself pause on it. That stars, entire stars, burning and massive and ancient, are themselves subject to the same principle that would slow a clock carried by a falling traveler. That the universe applies its rules without exception, without scale preference, without distinguishing between the very large and the very small in the matter of how time behaves near mass. A star orbiting a galactic center and a hypothetical traveler orbiting a stellar black hole are subject to the same geometry, the same curvature, the same slowing of duration that general relativity describes with such elegant and indifferent precision. Indifferent is perhaps the right word. The universe does not slow time near massive objects as a gift or as a punishment or as a feature installed for any purpose. It does so because of what time is. Because time is not separate from space, not an independent stream running alongside the three dimensions we can point to, but woven into them, part of the same fabric, subject to the same curvature that mass produces in space. When Einstein arrived at this understanding, when the full structure of general relativity became clear in 1915, it was not immediately obvious how strange its implications were. The equations were beautiful. They were consistent. They reduced to the Newtonian picture in the regime where Newton's picture worked well. But the regime where they departed from Newton, the regime of extreme curvature and high velocity, led to conclusions that took years, decades, to fully absorb. Black holes were initially considered mathematical curiosities, artifacts of the formalism rather than predictions of real objects. The possibility that time could run at meaningfully different rates in different places was treated with a philosophical suspicion that scientific communities sometimes extend toward ideas that feel too strange to be physical rather than merely mathematical. And yet the strangeness persisted. It survived every test. It embedded itself in technology, in navigation, in the daily functioning of systems that billions of people use without thinking about the relativistic corrections built into them. The strangeness turned out to be the reality, and what had felt like familiar certainty, the absolute tick of a universal clock, the fixed and common rate of time's passage, turned out to be the approximation. A very good approximation, accurate enough for all ordinary human purposes, but an approximation nonetheless. The universe beneath the approximation is stranger and richer and more textured than the approximation suggests. This is a pattern that recurs throughout the history of physics, and it is worth noticing, worth holding in mind as a kind of orientation toward the unknown. The map that works for ordinary purposes is not the territory. The territory is always more detailed, more surprising, more willing to exceed the boundaries of the map than we expect when the map is working well and we have stopped checking its edges. Newtonian mechanics was not wrong. It was incomplete. Classical electromagnetism was not wrong. It was incomplete. The picture of time as absolute and universal was not wrong for the purposes it served, for the scales at which it was applied. It was incomplete. And each time the incompleteness was discovered, it was discovered at the edges, in the places where the map ran out and the territory kept going, indifferent to the fact that we had not yet drawn it. We are likely in a similar position now. General relativity and quantum mechanics, the two great frameworks of modern physics, both work extraordinarily well within their respective domains. General relativity describes the large scale, the massive, the curved geometry of spacetime around stars and galaxies and black holes. Quantum mechanics describes the small scale, the behavior of particles and fields at distances so tiny that the word tiny becomes inadequate and the mathematics has to carry the meaning instead. Both are tested to extraordinary precision. Both make predictions that have been confirmed with an accuracy that exceeds the demands of any practical application. And yet they are not reconciled with each other. At the places where both should apply simultaneously, at the center of black holes, at the earliest moments of the universe's history, at the boundary conditions where quantum fields exist in regions of extreme spacetime curvature, the two frameworks produce results that cannot both be correct. The map runs out, again. The territory continues, again. And we are left, again, at the edge of what we know, looking out into a region we can describe only partially, only approximately, only with the awareness that the description is being held loosely, in an open hand. There is a particular quality to scientific humility that is different from ordinary uncertainty. Ordinary uncertainty is uncomfortable, something to be resolved as quickly as possible, a gap in knowledge that feels like a deficiency. Scientific humility, at its most mature, is something else. It is the recognition that the gaps are not failures but invitations. That the places where the map runs out are the most interesting places on the map. That the questions which cannot yet be answered are, in some important sense, the most valuable questions available, because they point toward the territory that has not yet been drawn, toward the understanding that does not yet exist, toward the next revision of the picture that will itself eventually be revised as the edges are found again and the territory beyond them is, slowly, patiently, carefully mapped. This is the work. Not the arrival at final answers, but the movement toward better questions, the refinement of the map through the honest acknowledgement of its edges, the willingness to stand at the boundary of the known and look outward without pretending to see more clearly than the evidence allows. It is slow work. It is cumulative work. It is work that no single mind completes and no single generation finishes, work that passes forward through time the way light passes through space, carrying information across distances that exceed any individual life, arriving somewhere it was always traveling toward without knowing the name of the destination. And perhaps this is where the physics and the personal converge most quietly. Because we are all, in our own way, doing a version of this. Moving through a universe we did not design and do not fully understand, accumulating the map as we go, passing what we have learned forward to those who will continue past the point where we stop. The traveler who falls into deep gravitational time and returns to find centuries elapsed is an extreme version of something that is true in smaller ways for everyone. We all return, in the morning, to a world that has continued while we were absent from it, while we were sleeping, while we were elsewhere, while we were inside the private duration of our own experience. We all carry memories of a world that no longer exists in exactly the form we remember. We all navigate the gap between the map we have and the territory that keeps moving, keeps changing, keeps exceeding the drawing. The universe is approximately 13.8 billion years old. This number is large enough that it resists comprehension in the way that very large numbers always do, becoming a symbol rather than a quantity, something you point to rather than something you hold. In that time, the matter that would eventually become you has been part of stars, has been scattered by supernovae, has drifted through interstellar space, has been gathered by gravity into a planet, has been incorporated into the slow chemistry of a biosphere, has moved through countless forms before arriving at this one. The atoms in your body are old in a way that your body is not. They carry a history that began long before there were eyes to see or minds to understand what was being seen. And here, now, for a brief and improbable interval, some of that ancient matter has arranged itself into a shape that can ask questions about the nature of time. That can lie still in the darkness and consider the behavior of clocks near black holes. That can feel something, some quiet and nameless thing, when it contemplates the distances and the durations and the strange geometry of the universe it finds itself inside. This is not a small thing. It may be the least small thing there is. Because the universe, as far as we can determine, does not contemplate itself except through the arrangements of matter that develop the capacity to do so. The awareness that exists in you, the one that is following these words through the quiet, that is perhaps growing slower and softer at the edges as sleep approaches, that awareness is the universe's way of being known to itself, partially, imperfectly, beautifully, incompletely. You are not separate from the thing being described. You are made of it. You are a local region of space-time that has become curious about space-time. A temporary arrangement of matter that has developed the ability to wonder about matter. And the wondering itself, the capacity for it, the fact that it exists at all in a universe that did not have to produce it, is perhaps the deepest mystery of all, deeper than black holes, deeper than the curvature of spacetime, deeper than the question of what time actually is beneath the mathematics that describes its behavior. We do not know why there is something rather than nothing. We do not know why the constants of nature have the values they do. We do not know what lies beyond the observable universe, or what came before the conditions that produced the beginning we can describe, or whether the word before even applies to whatever preceded the existence of time itself. These are not questions with answers currently available. They may be questions that will never have answers available, not because the answers do not exist, but because the tools required to reach them lie beyond what any mind operating inside the universe can construct. We hold them loosely. We carry them forward. We pass them on. And in the meantime, the stars continue their slow burning. The black holes at the centers of galaxies continue their patient accumulation of mass. The universe continues its expansion into whatever it is expanding into, carrying all of this, every galaxy and every void and every brief arrangement of matter that has ever looked up and wondered, outward and outward and outward into a future that has no edge we can see and no ending we can calculate. Time continues, unevenly, at different rates in different places, slower in the deep wells of gravity, faster in the open spaces between galaxies, but continuing everywhere, in every frame, in every clock, in every heartbeat of every creature that has ever existed in this old and surprising and improbably beautiful universe. And you are here, inside it, breathing slowly, at the edge of sleep, carried forward, gently, by the same time that carries everything. Let it take you. There is nowhere else to be, and the universe will continue its quiet work while you rest inside the small and perfect duration of this night.